Hello. In this video I want to talk about the polar form of a complex number. So now what is the polar form? Well, it's just a different way of representing a complex number, right? So at the moment we have the standard form for a complex number. Z is a plus bi. And the polar form is just a different way of representing a complex number. And it's essentially like the polar coordinates for a point in the plane. And it turns out to be extremely useful whenever we're dealing with problems involving multiplication. Right. Now, first a little theorem. So, we take two real numbers, p and q, and p squared plus q squared is 1. Then there is exactly one number, theta, sitting between minus pi and pi, with minus pi excluded and pi included, so that p is sine theta and q is cos theta. Right. Now, where does this number theta come from? Well, it's actually quite simple. We take our two numbers p and q, and we take the point qp in the plane R2, and we look at the ray going from the origin through this point, and we take the ray going from the origin through the point 1, 0. So in other words, through the x-axis. Okay, so in other words, this ray is the positive x-axis. And now we look at this angle formed by these two rays, and we look at its magnitude alpha. Now, if p is bigger or equal to 0, we simply take theta to be alpha. If p is less than 0, then we take theta to be minus alpha. Right. And that's where we get this number theta from. Now, an immediate consequence of this is the following. Right? If we take a non-zero complex number z, right, then we can find exactly one number theta between minus pi and pi, again with minus pi excluded and pi included, so that we can write z in the following form. Z is equal to r times cos theta plus I sine theta, with r being the modulus of z. And it's very easy to see. We just apply our previous theorem with q equal to the real part of z over r, and p the imaginary part of z over r, right? And this follows immediately. Now, this theorem has a very nice geometric interpretation. Yeah. So here we've drawn the picture in the case where the imaginary part is positive, right? So what have you got? Again, we look, here's the complex number 0, there's z, we look at this ray, we look at the positive real axis there, and theta is just the angle or the magnitude of this angle, right? So in this little right triangle here, the hypotenuse has length r, this side here has length a, and that side there has length b, right? So then if theta is the magnitude of that angle at 0, then it's basic elementary trigonometry that the cosine of theta is adjacent over hypotenuse, and the sine of theta is the opposite side over hypotenuse, right? Now, of course, if the imaginary part is negative, then our theta will just be minus the magnitude of this angle. Right. Now, this leads us to the polar form. So, a polar form for a complex number z is, well, it's just a different way of representing the number. Right? So, if we can write z as r times cos theta plus I sine theta for some real number theta. This is for z non-zero, then this is a polar form for z. the case where z is 0, we just take z is 0 times cos 0 plus I sine 0. And in fact, having theta equals 0 here doesn't matter. The important thing is just that the r must be 0. Okay, so from this equation for z, it follows that the real part of z is r cos theta, the imaginary part is r sine theta, and the modulus of z is r. Okay, now a couple of things you need to note. Right, remember, the sine and cosine functions are periodic with period 2 pi. Right? So if you've got your z in polar form, z is r cos theta plus I sine theta, then z will also be equal to r cos theta plus 2 pi k I plus I sine theta plus 2 pi k for any integer k. So that means that we have many polar forms for a given complex number, right? Once we have one polar form, we can just add any integer multiple of 2 pi to theta, and that gives us another polar form for the complex number. Right? But our previous theorem tells us that there's just one theta that sits in the interval minus pi pi, right? And this value for theta, right, that one theta in minus pi pi, we call the principal argument of z, right? So the polar form is also sometimes called the modulus argument form, right? That's because here we have the modulus, and this theta here we call the argument, right? And the theta that sits between minus pi and pi, we call it principal argument. Right, so let's look at a quick example. We want to write the complex number z is 1 minus root 3I in polar form with principal argument. Right, so obviously the first thing we need to do is get r. And r is mod z. And so that's going to be root of 1 plus 3 root 4 is equal to 2. Right. So now our job is find that unique value for theta between minus pi and pi such that z is r cos theta plus r sine theta I. Right. So in other words, we want 2 cos theta to be equal to the real part of z, which is 1, and we want 2 sine theta to be equal to the imaginary part of z, which is minus root 3. So this equation becomes cos theta is a half, and this equation becomes sine theta is minus root 3 over 2. Now remember, theta is between minus pi and pi, right? So that means each one of these two individual equations will have two solutions, and we are looking for the common solution, so the value for theta that satisfies both equations. Now if we look at cos theta as a half, then either theta is pi over 3 or theta is minus pi over 3. If we look at sine theta as minus root 3 over 2, then either theta is minus pi over 3 or theta is minus 2 pi over 3. Right. Now our theta must satisfy both equations. So we look at our solutions here and we extract the common one. So our value for theta minus pi over 3. So in other words, in polar form with principal argument, our z is r, which is 2 cos minus pi over 3 plus sine minus pi over 3i. Okay, so you must be careful when finding this value for theta. Right, remember, for each equation there are two solutions, and you need to extract the common one.